down here, don't knock it over. I've done that before, once. I don't do it again once I have one thing happen once. Okay, so. We just did a solution problem. I want to go back and talk about this one again, okay? I already did our first solution problem here. I already did have one, I think one or two of those also in the exercises for this activity that you did on Tuesday, right? So if you could look at this and figured out yourself how to do this, it's in the book as well. Let's talk about this. You have 50 mils of 3 molar sodium hydroxide. You want 0.5 molar sodium hydroxide. What do? Well, you know. Concentrated or dilute, you add water to it, right? How much water? How do we figure it out? Well, as we just talked about, we use our dilution equation. And this one here, instead of having to write all this stuff out, I have it written in the notes. There's my initial volume, or initial, molarity, 3 molar, right? My more concentrated one. There's my initial volume, 50 mils. My final molarity, and I want to figure out my final volume just like this one, honestly. It's the same one, but just different numbers, right? And we don't always have a situation we're trying to figure out V2 or VF. This is just similar to what we just did here. So I plug my numbers in, do my algebra, here's what I come up with. 300 mils, right? Which what that means, once again, just like the example we did, it doesn't mean add 300 mils of water. What it means is this. We already have 50 mils of water, don't we? In that solution, or 50 mils total volume in our concentrated solution here. Where'd it go? Here we go. That's 3 mol. Oh, problem's on the other page. Just a minute here. Let me go back and show this again. You have 50 mils of the 3 molar solution. So we already have 50 mils, don't we? So it should make sense that we're going to add 250 mils of water, just like we added the 306 to our last example, right?
Yeah.
So we add 250 mils of water, or we can just say, take our 50 mils of our 3 molar solution and add water up to the 300 milliliter mark. Either one's fine, right? That's how we do that dilution. So most people like dilution problems because they're kind of simple. Just figure out that it's dilution, use your equation, do the algebra, and figure out those numbers. We have to also realize what it means, okay? And just so you know, was there a problem in the exercises for the molarity, exercises that asked you to describe how you make that solution? There was. Just so you know, I have asked questions on exams before where I say, you know, calculate this number and then tell me how you would make it. I've done that many times. So it's not just, can you do the math? Does it make sense to you what you're supposed to do, right? Okay, any questions about that last example or anything so far? Okay, we're going to change gears a lot, completely change gears. We're going to continue talking about concentration and specifically molarity, but now we're going to talk about molarity with stoichiometric calculations. I'm going to get all this stuff erased. Start with a clean whiteboard. There we go. Okay. Looks like it's having a hard time focusing today. There we go. Okay. Before I do this problem, I'm going to have you read it while I'm writing something on the whiteboard here. There's a poster for that. Oh, I don't need it actually. So in chapter 4, we use this outline quite a bit. Grams of A to moles of A. I'm going to put double-headed arrows here now. Moles of B. Grams of B. Okay. Remember this from chapter 4, stoichiometric calculations? So if you have a balanced chemical equation, if you know the mass of substance A, a reactant or a product, you can figure out the moles of substance A using what conversion factor? Can you remind me?
Mass.
Molar mass, right? Molar mass of what? A, of course. So I'm using capital M, little m for molar mass. So capital M by itself is molarity, right? If I have a balanced equation to go from moles of substance A to moles of substance B, how do I do that again?
The ratio and the balance.
The mole ratio from the balanced equation. Hopefully everyone in the room is going, yeah, I know that. I'll put mole ratio. I'm not gonna tell you it's A and B, we already know it's gonna be A and B molar ratio. Can you read that okay, people in the back? Mole ratio, okay? And how do I go from moles of B to grams of B again?
Molar mass of B.
So molar mass of B. That part's not new. Molarity, however, molarity is units of moles per liter is a newer topic for us, right? So let me show you something. I'll write a little outline here and then we'll start this problem. Volume of A. I'm gonna write the whole word molarity, I think, is that clear? Molarity of A. So here we're using molar mass of A as a conversion factor, the mole ratio from the balance equation as a conversion factor, right? And molarity B or molar mass of B as a conversion factor. What I did here is I put a couple extra arrows here on my overall outline that we already used numerous times for stoichiometric calculations. So now we're going to be using stoichiometric calculations with molarity, solutions that have certain concentrations and perhaps known volumes or unknown volumes. So here I have volume of A, moles of A, use molarity of A as a conversion factor. Volume of B, molarity of B, use molarity of B as a conversion factor, yes.
So is the mole ratio the same as the molarity ratio?
Well, this one comes from the balance equation.
Mm-hmm.
This one comes from the concentration of whatever that solution is for that
Right.
substance A or B.
But the molarity of A and the molarity of B, that ratio is the same as the mole ratio?
No, those are concentrations, so it's not the same. So you have to use a mole ratio from the balance equation here. The molarity just goes between these two,
Okay.
okay? Okay, so with that outline on the whiteboard, let's talk about this next problem, because these can be a little more challenging. Magnesium reacts with acids to produce hydrogen gas. If you have 5 grams of magnesium, what volume of 0.1 molar nitric acid is needed to convert the magnesium completely? Well, to do a problem like this, we're having magnesium react with nitric acid to produce some hydrogen gas. This is a chemical reaction that's being described in this sentence, I guess. Just one sentence, or 2 sentences. You know what that means? I need to write out, as it says here, write the balanced equation. And we talk now about metals reacting with acids. A little bit, well anyways, I'll just explain this right now. So we have magnesium metal. Did you use magnesium metal in lab last week?
Yes.
Yes, you did. You reacted magnesium metal with what acid? Can you remind me the acid?
Hydrochloric.
Hydrochloric acid. Here we're using nitric acid. So instead of using hydrochloric, I just write HNO3 because magnesium metal reacts very readily with strong acids. So I have my 2 reactants. It already tells me we're going to have some hydrogen gas, just like you had in lab last week, right? The other thing I have to figure out is what is the other product? Well, here I have HNO3, not HCl. What do you think the formula for the other product that may be formed could be, based upon the fact that you know that magnesium is going to lose some electrons? I'm telling you that right now, it's going to lose electrons. How many electrons do you think magnesium might lose? Based upon where magnesium is located in the table? 2. So it's true, it's going to form magnesium plus 2, right? What's the charge of a nitrate anion? -1, right? So I memorized it, right? So my formula for the other product that's going to be formed is MgNO3 Magnesium metal turns to magnesium plus 2, which then dissolves in the solution. You cannot see it, it's still there, it's just dissolved, right? There's the cation. So there's my reactants, there's my products. Is this chemical equation done? Is it all ready to go for this problem? What's not done about it?
It's not balanced.
Is it 3 or 2?
I don't,
Oh, it is a 2. Did I?
Okay.
I wrote a 3. What's my problem today? Yes, it's not. Thank you for noticing that was a real mistake. It should be 2 because magnesium is plus 2, nitrates minus 1. I said that and then I wrote a 3. Who knows what's going on in my brain today? Okay, so what's not done with this besides switching that 3 to a 2? Because that
Not
was
balanced.
incorrect. That was a real. Sometimes make mistakes on purpose for you to catch them. This was a real mistake. I did not mean to write 3. The wrong formula. Now we have the right formulas, right? you tell me one more thing I need to do with this?
It's not balanced.
It's not balanced, thank you. I know you said I just wanted to have everyone think about it. Okay, so I have 2 nitrates over here, only 1 here, so it's pretty easy to balance, put a 2 in front of that. And I'm balanced, aren't I? Okay, so you need to have a balanced equation to use to do this problem, because what I'm doing here is, as you can see in the title, solution stoichiometry. So we're still going to be using this stuff up here, right? But we're also going to be using molarity, because we have a concentration, don't we? So, you'll notice I'm given the mass of one of my reactants. I'm also giving the molarity of my other reactant. I'm going to start with my mass of magnesium. So question mark moles of magnesium equals 5.00 grams of magnesium. So I'm given 5 grams of magnesium that's going to react, right?
Right.
So that's my grams of A, isn't it?
Yes.
How do I go from grams of magnesium to moles of magnesium? Can you remind me how to do that?
Find the molar mass of magnesium.
Find the molar mass of magnesium. Look it up here.
24.305.
20.31. Making sure I use my units so I know I'm doing the math correctly. So I'm dividing by the molar mass, not multiplying, right? So I write my units out.
Right.
So I do that math, I'm going to get the moles of magnesium. Would you agree with that? Now I have this stepwise in the notes here. I'm going to just not write the answer to that. Just go through this step by step in the notes. So I have my grams of magnesium, reduced to moles of magnesium. What I'm trying to get to eventually, by the way, if you look at what's happening here, which I forgot to do here, it says what volume of 1.5 molar nitric acid is needed to convert magnesium completely, right? So what I'm trying to get to eventually is volume of B, right? Make sense what I'm talking about? My B is my HNO3, but I want to get to over here, my volume of HNO3. So right now I went from grams of A to moles of A. So my next step is to relate magnesium to HNO3. How do I do that? Here's my step it tells you. Well, it tells you right there in the notes. Use the stoichiometric ratio or the mole ratio. You can also see it up here, can't you?
Yes.
So what's my mole ratio here in this case? To go between magnesium and HNO3.
2 to 1
2 moles of HNO3,
over 1 mole.
1 mole of magnesium, and I get that from right here. That's where I got that from, right? Now we can do one more step here, but I'm gonna just calculate this answer because we're used to getting to here from previous calculations in chapter 4. So let's just get this answer here and think what we're gonna do next. Times 2. So here's what I get. Okay.
Yes.
So I get 0.41135. I'm not going to round right now, so I'm going to round at the end. And that's moles of HNO3, right? So far, so good? So we're right here. We have to get here. What does this outline tell me I need to do? Use molarity of B as a conversion factor. Just like molar mass was a conversion factor, the mole ratio from the balanced equation was a conversion factor, right? So I'm not going all the way to grams of B now because I don't need to do that in this problem. So I'm stopping here on this top line and I'm moving down. The problem tells me the concentration of the nitric acid is 1.50 capital M HNO3, right? That's the same thing as 1.50 moles per liter. So I'm going to change that into what it really is. So capital M means moles of HNO3 per liter of HNO3 solution. That's what it means. See that moles in liters? What do you see here?
Moles.
Moles, question mark, liters, HNO3 solution. That's what I want to find. Now it doesn't say liters, it just says what is the volume. I'm deciding to use liters for my volume, okay, units. So far so good?
Yes.
Can someone tell me what to do here?
So you invert the ratio and plug it into your.
Exactly, invert that molarity and use it as a conversion factor like we've been doing for molar mass and molar mass especially. Sometimes the grams on top, sometimes on the bottom, right? So we're using molarity as a conversion factor. We're going to go 1.50 moles HNO3 to 1 liter. My moles cancel out. My liter does not, and I will get liters of HNO3 solution. So let's plug that in. I already have my calculator answer, I didn't round it. Divided by 1.50. 0.274 liters of HNO3 solution is needed, which is equal to 274 milliliters if you want to switch it to milliliters. So people get this answer? I didn't ask. Is this the right answer? I did that math?
Yes.
Yeah.
Make sense? Okay. Let's do one more. Yeah, I'm gonna do one more because this is a hard topic. Okay, this one I'm gonna have you try to do. No, you know what, I'm changing my mind, never mind. I'm not gonna do one more. I'm looking at the clock. No. We're gonna move on. We're gonna do some more of these calculations later with titrations with acids, so. Okay. Any questions on the problem behind me right now? Yes?
So with the conversions that we have, when do you use molarity A and use molarity B?
Say that again?
When do you use the molarity of A as a conversion factor?
Well, I mean, realistically, if you're, sometimes you find that you don't have grams of A, you might be given, for example, molarity of A in volume, and you're gonna have to use those here to get this, right? Depends on your problem. So this time I started with grams and I went down like this, but sometimes you're not gonna give them, given a mass, you'll be given a concentration and maybe a volume, and you have to figure out moles of A from that.
So if you had grams and you wanted to find the volume of A, which is grams, then moles A and a volume A.
Right, yep, you can do that. Yep, and that would be just that kind of thing we were already doing
Right.
in the activity. So this part of this is actually kind of what we're doing in the Chemotivity 32 activity. Already grams to moles to volume using molarity, right?
Yeah.
Or we went like here more, that direction. But so the one I just did here went like this, right? But you'll notice that I also have this one here that sometimes we have problems, we have to go like here in this direction. Okay. So our next topic is types of aqueous solutions and solubility. And as we have already been talking about, many reactions of ionic compounds take place in water. We haven't talked about it officially, I haven't said that, but we've seen the AQ phase label a lot, right? Okay, so I'm going to put this right here. Okay, there we go. Oh, my cord out of the way. So you can see I have a light bulb here. Even though I just plugged this in, the light bulb did not light up. The reason it did not light up is because you can see those copper electrodes that are sticking down. Are they touching? No, they're not touching. So therefore, right now the light bulb is not lit up. To make this light up, I'd have to have those electrodes touching or do something that electricity could actually be conducted between those electrodes. Okay, I'm gonna turn off a few lights for this, just to make it a little more fun. Even though our window's open, it'll be darker than still pretty light. What I have here is I have some tap water. Okay? And what I have here is some deionized water. So while you guys are taking the quiz, I put some tap water from this tap into this beaker. I put some deionized water from this gray tap, which is our deionized water system that we have, the filtration system downstairs. I'm going to see if I can get this light bulb to light up. So deionized water has no ions in it. The ions have been removed. It's just water. It could be some other organic compounds that don't form ions, but there's no ions. Let's see what happens if I put these electrodes in this deionized water. First, let me ask you, how many people think that the light bulb's going to light up? Nobody. We'll see if you're all right. Anything happening at all?
No.
No, nothing happening at all. Now I have some tap water. And tap water has a small amount of dissolved ions. You might notice when you have a tea kettle on the stove and you use it over and over again, you get some white crusty stuff in your tea kettle. You know what I'm talking about? Okay, that's those ions that don't evaporate away. Let's see what happens when I put this tap water. What happens? Lights up a little bit. Not lighting up a whole lot because I don't have a whole lot of ions in tap water, but I do have some. And those ions allow the electricity to be conducted. So when water doesn't have any ions in it, the electricity will not be conducted. Yes?
Is salt water even more conductive?
Oh yeah, for sure. In fact, I'm going to make some up right now. So in fact, I'm going to find my beaker that's labeled NaCl. So here I have a beaker, NaCl. doesn't have any seal in it yet, but it's going to have it soon. I'm gonna put some DI water into this beaker. I'm gonna pour some salt in it, just from kind of, bought that from Target, I think, because it's everyday essential, right? And what's gonna happen when I put my salt into the water? You know what's gonna happen, it's gonna dissolve, right? As long as I don't add too much, it should all dissolve. So once I do that, my sodium cations are now surrounded by a whole bunch of water molecules, each one separates, right? And my chloride ions also are now surrounded by a whole bunch of water molecules. So even though it may seem like that salt eventually disappears once it all dissolves, it's not. It's in there, isn't it? We know we can taste it, we can taste salt water. So now we have a whole lot of ions in this solution, don't we? The reason it's so cloudy because I put a lot of air in there, it takes a while to dissolve, but let's see what happens when I put, well, lights up a lot. Because you know why? I have way more ions in this solution than I had in that tap water. Remember, I started with DI water first, it didn't light it up. Okay, so when an ionic compound dissolves in water and 100% dissociates, or close to 100% dissociation, we make what's called a strong electrolyte. And a strong electrolyte will conduct electricity, as you can see. Now, of course, if I put less salt in here, I would have, my light bulb wouldn't light up as much. If I put even more salt, and if I got more dissolved, it would make the light up a little brighter. So more ions, more electricity flows. Because electrons can flow fast, more quickly, because you have more ions to basically transport those electrons in that solution. But even if the concentration of the sodium chloride was lower, and the light bulb didn't light up as much, it's still considered a strong electrolyte, because to be a strong electrolyte, you just have to have that compound dissociate 100%, okay? So I put 100 formula units of sodium chloride in solution, I get basically 100% dissociation of those formula units. Now, it's not just ionic compounds like, there's a lot of stuff in here, just a second here, where's my HCl there? Oh, there it is. I don't know if you can see this on the screen. What does that label say? 1 molar HCl. Oh, great. I can't get it open. I didn't test that out ahead of time to make sure I could open it up. Well, I'm going to skip that one because I can't open it. Let's try this one. I'm going to just tell you what happens, okay? This HCl is a strong acid. If I poured it in here and I could actually get this into the container, I would get a very bright light bulb. You just have to believe me on that one. So strong acids also 100% dissociate, and they also form strong electrolytes. Luckily, I can open up my sodium hydroxide container. I'll pour the sodium hydroxide in here. So sodium hydroxide, even though it's a base and not just an ionic compound like NaCl, I have a bunch of sodium cations floating around, a whole bunch of hydroxide ions floating around. What do you think is going to happen when I put the electrodes in this sodium hydroxide solution? It's going to be very bright, and it is. So strong acids, 100% dissociations are strong electrolytes. Strong bases that 100% dissociate also are strong electrolytes. And just your average ionic compound that 100% dissociates is a strong electrolyte. What does this say? Vinegar. You know what vinegar is? Vinegar is a solution of acetic acid in water. And acetic acid is a weak acid. And what that means is that when you, let's say you have 100 molecules of acetic acid, only like a few % of those will actually dissociate into H+ and the acetate anion. Okay? So it's a weak electrolyte. So even though I put a lot of this in here, and it's, watch what happens to my light bulb. Does it light up a lot? No, it lights up a little bit because even though if this 100% dissociated, I would have a very bright light bulb. But it doesn't. It only dissociates a tiny bit. And that's called a weak electrolyte. So it's an ionic compound that dissociates only a small amount and is a weak electrolyte. Okay, 2 more examples. Does sugar dissolve in water? Yes, it does. So I'm going to put in some water into another beaker. I'm going to put some sugar in here. Even though we all know this is going to dissolve, I'll put lots of sugar in here. Notice I put deionized water, not tap water in here. If I put tap water, I'm going to have a few ions in there. I'm going to just pile in the sugar here. So sugar is very soluble in water. I can put lots, I just spilled a little bit. I can put lots of sugar in here, get this to dissolve. Of course, it does take a little bit of time to dissolve, but I definitely already have some dissolved. So we know sugar dissolves from everyday life, and we just saw me dissolve it right now. What's gonna happen when I put these electrodes in this sugar solution? What do you think? I hear nothing, and the nothings are correct. But didn't it dissolve? Everything else that dissolved in solution made the light bulb light up, didn't it? So what's going on here? What's going on here is this. Sugar is a molecular compound that dissolves readily, but does not form ions. So if you have a molecular compound that dissolves, which many of them do, not all of them will dissolve in water, but many do because of some solubility properties, and I'm not gonna go into the details of why, but they do, but no ions are formed, you will have a non-electrolyte solution. This is still a sugar water solution. If I drink it, which I'm not gonna do because it touched that electrode, but if I did, I could taste sugar, right? Okay, so any molecular compound that dissolves in water that does not dissociate into cations and anions will form a non-electrolyte solution. What do I have here?
Gatorade.
Gatorade's actually G2, so it's the low-calorie version. Just grabbed this from home, actually. What do they say about Gatorade when you talk about, when you hear advertisements about Gatorade? They replace your electrolytes. What have I been saying today so far in the last 10 minutes or so? Strong electrolyte, weak electrolyte, non-electrolyte, right? So Gatorade, this G2 probably has some NutraSweet or some, non-calorie, zero-calorie sweetener. But it also has other ionic compounds in there that we need for life. So that's what happens when I put the electrodes in the Gatorade. So it's not just the NutraSweet, okay? Because NutraSweet, by the way, is not an ionic compound. It's a molecular compound. So is Splenda, so is all the other ones we talk about, we might be using. So what's causing that light bulb to light up are the ionic compounds that are in Gatorade. Why does Gatorade have ionic compounds in it? Because when you sweat a lot, you ever do a lot of exercise, you ever get like, honestly, it's kind of gross, but you ever get like kind of a crustiness after your skin evaporates on your arm? Because you've lost ionic compounds from your body, especially sodium and chloride, okay? So if you sweat too much and exercise too much and don't replace not only the water you lost, but also some of those cations and anions that you lost, you can die. And in fact, if all you drink when you're doing a lot of exercise, just drink water, and don't eat anything to get more ions in your body, your heart actually doesn't have enough ions to function correctly, and you can have a heart attack and die, and other things go wrong too, and it's not a good thing. Anyone know the history about who developed Gatorade or how that came about? It was Florida State Gators. It was a football team. Okay? They were doing a lot of exercise in hot, humid Florida. They were just drinking water, said, oh, we got to get more than just water, so someone just made up Gatorade. I don't know the whole history of it, but that's where it came from. That's why they call it Gatorade. Now, of course, we also have Powerade and other things now besides Gatorade, but that's why we need to replace our electrolytes. Okay.